Early computation was defined by its physical mass. To perform a few thousand operations per second, these machines required tons of steel, glass, and dedicated cooling systems. Today, that same capacity exists on a silicon surface smaller than a fingernail. This is a microscopic view of a modern microprocessor die. It contains more interconnected functional zones than a city, despite measuring less than 2 centimeters across. Within these geometric grids, millions of logic gates operate simultaneously, routing electrical signals through pathways only nanometers wide. Contrast that density with Jack Kilby's 1958 prototype. It is a single sliver of germanium, roughly shaped and held together by hand-soldered joints. The evolutionary gap between these two objects illustrates a hardware reality. As computation grows more complex, the number of required switches increases exponentially. Before the transistor, those switches were vacuum tubes. They relied on thermionic emission, burning hot enough to boil electrons off a metal filament and consuming enormous amounts of power in the process. Jumping from a few hundred glowing glass tubes to billions of invisible switches required more than just shrinking the parts. It required a new way to connect them. The solution was the monolithic circuit, a method of manufacturing where the components and their wiring are fabricated as a single continuous unit. We will track the engineering path from the first solid-state crystals to the birth of the planar process. By mastering the physical interconnection of parts, engineers successfully moved computation from the world of massive hardware into the realm of microscopic logic. The first major step toward miniaturization was the solid-state transistor, the engineering successor to the vacuum tube. Unlike the vacuum tube, a bipolar junction transistor passes current through a solid crystal. There's no glass bulb to break and no heating filament. Because it didn't rely on heat, the physical size and power requirements of the electronic switch dropped significantly. But while individual transistors were reliable, building a computer meant taking thousands of these discrete parts and wiring them together by hand. By the late 1950s, this manual assembly reached a limit known as the tyranny of numbers. Every connection had to be soldered manually. In a system with thousands of components, every solder joint represented a potential point of failure. As computer architectures became more ambitious, the statistical probability of a manual wiring error approached 100%. Even as the transistors themselves became more reliable, the failure rate of the systems built from them increased because of the sheer volume of interconnections. Without a way to connect these switches automatically, the scale of digital logic would have stalled permanently in the 1950s. In 1958, Jack Kilby, a newly hired engineer at Texas Instruments, proposed a radical theoretical solution to this seemingly impossible manufacturing bottleneck. Kilby realized that every circuit part could be made from the same semiconductor material. In his prototype, transistors are formed directly into the center of the germanium block, while the material's natural resistance is used to create passive components on the exact same sliver. This was the birth of the monolithic integrated circuit, a complete electronic system built on a single block.
However, Kilby's design had a significant flaw. To make these embedded components talk, he still had to bridge them with tiny gold wires. These gold wires required delicate manual placement under a microscope. While he had integrated the components, he had not yet automated the wiring. Kilby proved that integration was possible, but his method of using gold threads meant the manufacturing bottleneck remained. To reach true mass production, the industry needed to eliminate three-dimensional physical wires entirely. The ultimate solution to this bottleneck was the planar process, developed by Jean Horny and Robert Noyce at Fairchild Semiconductor. They started by flattening the silicon substrate and embedding the active PN junctions entirely beneath the top surface. They then grew a layer of silicon dioxide over the top, creating a chemically protected, perfectly flat surface. This flat surface allowed engineers to use photolithography, literally printing the circuit patterns using light. Instead of using gold wires, they etched channels into the surface and deposited metal into them, creating integrated traces connecting the buried components. These printed metal connections were flat, stable, and completely replaced the need for manual wiring.
Because the process was photographic, hundreds of complex chips could be printed simultaneously on a single wafer. This transition from 3D assembly to 2D chemical printing is the process that still manufactures every modern chip today. By turning wiring into a printing task, the physical limits of mass production were permanently removed. With the interconnect problem solved, the number of components per chip began to double every few years. To keep up this pace, the industry shifted from early bipolar transistors to metal oxide semiconductor, or MOS, technology. Early bipolar logic gates were relatively large and generated significant heat. MOS transistors could be made much smaller. Modern CMOS architecture draws significant power only when switching, allowing millions of transistors to operate without overheating. This efficiency is what allows engineers to pack millions of transistors into a space that doesn't melt under its own power demands. The technology scaled from 100 component chips in 1960 to microprocessors with over 2,000 transistors by 1971. This Pentium die is the result of that scaling, an organized grid of millions of MOS transistors working in unison. By shrinking the switches and automating the connections, engineers transformed computing power into a predictable, rising curve. In the modern era of very large-scale integration, the physical work of wiring those millions of connections has been completely and fully automated. Because of the planar process, engineers no longer have to worry about individual solder joints or manual wire placement. The physical constraints of 1950s manufacturing have been abstracted into pure mathematical logic. Chip designers now use Boolean algebra and advanced software to arrange millions of transistors as blocks of logic. Microscopic switches are now treated as abstract data points rather than fragile physical objects. By solving the physical interconnect bottleneck, engineers successfully moved computation off the assembly line and into the era of digital logic.